Hi students, in this lecture I am going to discuss problems based on dielectrics. Let us see first one. See the question carefully. Figure shows a parallel plate capacitor with the plates of width B and length L. The separation between the plates is D. The plates are rigidly clamped and connected to a battery of EMF V. A dielectric slab of thickness D and dielectric constant K is slowly inserted between the plates. Calculate the energy of the system when a length x of the slab is introduced into the capacitor. What force should be applied on the slab to ensure that it goes slowly into the capacitor? Neglect any effect of friction or gravity. See diagram once. So it is a capacitor. So these two are the plates which is connected to a battery. And you can see here a dielectric substance which is now filling the space between the plates. Now it is x length is inside. So first we have to calculate energy of the system when a length x of the slab is in the capacitor. Let us see how to get it. First, let us make the diagram. So it is a capacitor. So between the capacitor plates, so we are connecting a battery. So battery is now connected. Its EMF is given as V. Now between the plates of the capacitor, we are placing a dielectric. So we are placing a dielectric. You can see here. This is now dielectric. And given length of the plates, that is L, length of the plates. And here X part is now inside. X part is inside. So coming to the question, first one, calculate the energy of the system, right? So coming to the first part, energy. See what we can do energy. Since the battery is connected, it maintains a constant potential difference. And we're having potential energy equal to, it is equal to half CV square, right? Now we have to focus what is the capacitance of this system. It is what is the capacitance of the system. So now this can be taken as a combination of two capacitors. You can see the part of the dielectric which is now inside. This is just like one capacitor. Okay, it is just like a capacitor which is completely filled with dielectric. Okay, and remaining is now air capacitor. That means this is now air medium. And you can see across these two plates, we have same potential difference. That means capacitance is written as C equal to. So coming to here area, so what is now area? Width is given as B. So width is equal to B, length is L, right? The X part is now inside. So capacitance equal to K into epsilon naught. Coming to area, it is taken as B into X. See carefully. Width is given B. This length equal to X. So area equal to B into X. Epsilon naught A by separation equal to between the plates. Separation is given as it is D. Okay. So epsilon naught A by D. And we are having here dielectric constant, that is K. So K into epsilon naught A is B into X by D. Next, coming to air capacitor, it is air means K value 1, epsilon naught. Coming to area, it is L minus X into B, epsilon naught A by D. That is now capacitance of the capacitor. So take now this value here, then we get potential energy of the system. Okay. Or if you want, you can take here epsilon naught B outside, epsilon naught B outside, and D also outside. Remaining one is now X plus, see what we have here, Xk plus L minus X into B. Okay. That is now capacitance. Wait. Already we have taken B outside, right? B is already outside. Here B is not required. Right. That means this is now epsilon naught B by D Xk, and you are having X here. So remaining is now L plus X into K minus 1. That is now capacitance. Okay. Right. Now see the next part. The next part is what force should be applied on the slab to ensure that it goes slowly into the capacitor. Okay. Now first we have to focus why force is acting, means why we have to apply force on the dielectric. Let us see carefully. This is now capacitor. We are knowing that field is, so we are knowing that field is now, this is a positive charge, this is negative charge. Field is now like this, right? These are field lines. You can see field lines here. And we have learned that at the edges, field is now not uniform. It is a curved one like this. This is what we are calling as edge effect or fringe effect. Okay. So field is not uniform at the edges. Now, if we are placing a dielectric, if you are placing dielectric, see carefully. When we are placing dielectric, you can see here, I will make diagram separately here. So this is a positive, this is negative. When we have dielectric inside, so when we have dielectric inside, this is now dielectric. You can see this is now inducing here negative charge and here positive charge. But observe carefully. Field is now normal to plates like this. That means because of this field, there is no force. That means force is only normal to plates like this. So this is positive attracting this negative in this way, normal to plates. And this negative attracting this positive downwards. Okay. So force is only normal to plates. There is no force inwards. Okay. But if you observe carefully, see in this diagram, field is now at the edges. It is now curved one. And see here, this is a positive, this is negative, and this is a positive. Field line is a curved one. If you draw tangent, if you draw tangent to the field line, that is giving us direction of field at that point. See carefully. At this tangent, I am drawing, sorry, at this point, I am drawing tangent. Direction of field is like this. And at this tangent, or at this point, tangent is like this. Direction of field. Now, this is negative charge and the field is like this. So force will be now inwards. See carefully. I will take different color here to make it more clear. So since the field is now along the tangent at this point, force will be now like this because charge is negative. When force is like this, I will draw once again here one more diagram. Suppose this is now slab, dielectric slab. Having here negative charge, this is a positive charge. And we are having here field lines. Now they are curved like this. They are curved like this, right? They are curved. So at this point, I am taking tangent, which gives direction of field. At this point, taking tangent, that gives direction of field. Now you can see force acting on the negative charge. This is now negative charge. Field is in this way. So force will be opposite to field. This is direction of force on the negative charge. And this is a positive charge. Force will be along the field, right? That means the force is now like this. And you can take now components for these two into the capacitor. Component of these forces, it is into the capacitor. That means here force on the dielectric is because of the fringe effect. If fringe effect is not there, there is no force on the dielectric. That means into the capacitor. Because inside the capacitor, field is uniform and normal to plates. Then force will be normal to plates. There is no force along the capacitor, means into the capacitor. Okay. So force is into the capacitor because of the fringe effect, right? That means if you want to maintain uniform speed, or you can say constant speed, we have to apply force the same amount, but direction must be outwards. Okay. So your condition is, it is given that to ensure that it goes slowly into the capacitor. So goes slowly means we have to balance now this force. Okay. Then net force becomes 0. Then it goes slowly into the capacitor. Okay. So here conclusion is that there is a force on the slab into the capacitor because of the fringe effect. Because of fringe effect. So now we have to balance this effect, means this force. When we are balancing this force, then this moves slowly into the capacitor. Okay. Let us see how to calculate now that force. So we have to calculate now that force. Right, see how to get now that force. When dielectric is moving into the capacitor, when dielectric is moving into the capacitor, we have seen here capacitance is increasing when it is moving into the capacitor, right? When capacitance is increasing, potential energy of the system increases. So here potential energy means we are taking the dielectric and capacitor as a system. Okay. For that system, potential energy is increasing because it is now moving into the capacitor. Okay. So in this process, what happens is battery is doing work. So why battery is doing work means since capacity increasing, see carefully, Q equal to CV, B constant. As dielectric is moving into the capacitor, capacitance is increasing. Therefore, charge on the plates will increase. That means now more charge flows through the battery. That means by the battery work is done. Right? Now see carefully. We have to apply force on the dielectric. We have to apply some force on the dielectric to balance the inward force. So slab is now moving into the capacitor, but we are applying force outwards. So applied force is outwards, but displacement is inwards. So by external force, work is done, which is negative. Okay. So by this force, work is done. Work done by that force plus work done by battery. So this is now work done by external force. Okay. By the applied force and by battery. This must be equal to delta U plus delta K. So we have learned that in work energy power, work done by external forces is equal to delta K plus delta U, right? So here force is doing work, battery doing work. Sum of these two should be equal to delta U plus delta K. Now in this problem, it is moving slowly into the capacitor. Therefore, delta K equal to 0, right? Remaining is now delta U. Now see what is work done by applied force. Let us take it moves dx distance inside. Means at one instant it is now x inside. Now dx is going inside. Okay. Then by the force work is minus f into dx. Why negative means? Because the force is outwards, but displacement is inwards. Okay. That means angle is now 180 between force and displacement vectors. So minus. Next, by the battery, work done is positive because more charge is moving on to the capacitor. Okay. So charge is moving from low potential to high potential inside the battery. Right. Let us see how to write that. How much charge is flowing means. Let us say capacitance is changing from C to C plus DC. Okay. Then extra charge that is flowing will be given by extra charge dq, that is equal to change in capacitance into V, right? This is no extra charge that is flowing. So we can write as by battery work done is equal to its EMF is V into dq. This is the extra charge that is flowing through the battery because slab is moving inside. So this is equal to the place of dq. Take this value. It becomes now dc into v square, right? Now substitute here. It is a v square into dc. That is equal to du, or you can say delta u. I'm taking as du because So only small part is now going inside. So change is now du, very small, right? And we got here C value, sorry, we got here potential energy as a function of x, right? Now see how to get the value of du. Get the value of du. So du equal to, I'm taking from here, let us call this as 1. Differentiate equation 1. We get du, sorry, not differentiation 1. This is 1, okay? And 1, just a minute, this is right. So now we are differentiating equation 1. Then see what we get. It is a half C dc. V is a constant, so V square. Now substitute that here, okay? Then see what we are going to get. So we want f equal to Rf into dx, that is equal to V square into dc. I'm taking this one, okay, here, and this is now coming to here. V square into dc minus half dc into V square. So from this, see what we can write, f equal to, it becomes now dc and v square common, 1 minus half, it is a half. So half dc by dx into v square, or I can call it as, this is half c v square dc by dx, right? That means this is now change in the potential energy, right? Nothing but du by dx. Sorry, this is du by dx. That means that force acting on the slab, that is equal to du by dx, right? Now substitute the value of, so what is the value of dc by dx? Let us calculate here dc by dx, because if it is known, then force is known. Epsilon naught b by d, it is a constant. L is a constant, derivative 0, plus k minus 1, it is a constant, derivative of x, it is 1. Okay. Now substitute this value in this one. So force equal to epsilon naught b v square into k minus 1 upon what else left, d, and 2, right? It is 2d. This is the final answer. This is a force acting inwards, okay? It is an inward force. Or you can say this is a force which we have to exert outwards to maintain almost zero speed, means moving slowly. It is epsilon naught bv square into k minus 1 by 2d, right? I hope you got that clarity. In this, the main important point is it is moving inside because of the fringe effect. Okay, let us see next problem. Consider the situation shown in figure. The width of each plate is b. The capacitor plates are rigidly clamped in the laboratory and connected to a battery of EMF V. This is the battery. All surfaces are frictionless. Calculate the value of M for which the dielectric slab will stay in equilibrium. So this is just connecting with the previous problem. Okay. So in the previous problem, we got how much force is acting inwards, right? If that force is balancing this weight mg, then it will stay in equilibrium. See how much force we got there. So we got that force as epsilon naught bv square into k minus 1 by 2d. And remember, this is a constant force. It is not depending on how much length of dielectric is inside the capacitor. I am repeating, this force is a constant. It is not depending on how much length of dielectric is inside the capacitor. Okay. If this force is balancing weight of that block, then that block will be in equilibrium. So from this we get the mass, right? Mass of the block. So it is simply connecting with the previous problem, right? Let us see next one. Figure shows two parallel plate capacitors with a fixed plates and connected to two batteries. The separation between the plates is the same for the two capacitors. The separation between the plates. The plates are rectangular in shape with width B and lengths L1 and L2. The left half of the dielectric slab has dielectric constant K1 and the right half K2. Neglect any friction. Find the ratio of the EMF of the left battery to that of the right battery for which the dielectric slab may remain in equilibrium. So this is again basing on the previous result. We can see here force acting on this one inwards. If that is balanced by force acting on this inwards by this capacitor. I am repeating, force acting on this one by this capacitor, that is now into the capacitor. Force acting on K2 by this capacitor into the capacitor. If these two are balanced, then they will be in equilibrium, right? So condition is dielectric slabs may remain in equilibrium. Then see, right. It is now simply basing on the previous result. We can write force by the left one, epsilon naught b v square, epsilon naught b v square into, see how much we got, k minus 1 by 2d. So here in the place of k, k1, left one, right? If this is balancing, the other one is now epsilon naught b v square. Wait, actually it is given that ratio of EMF, right? We have to calculate ratio of the EMF of left battery to that of right battery. Okay, let us take left battery as VL, left battery, VR, right battery. Okay, into K2 minus 1, right one, upon 2D. Now you can see here, which we can cancel. Epsilon naught B by 2D. Epsilon naught B by 2D gets cancelled. We have to find ratio of their EMFs. So it is now VL by VR. Okay, that is equal to square root of K2 minus 1 upon K1 minus 1. Okay. So all these questions are basing on the same result. It is epsilon naught b v square into k minus 1 by 2d. It is a constant force, right?